Hi, my name is Nicole Riepl, and today I will be talking about imaging methodologies, specifically Raman spectroscopy. I want to start out by saying thank you to all the people on this screen, especially Faye Nicholson, for being such a great day-to-day mentor, and for Dr. Gwen for putting together such a comprehensive lesson plan for me that allowed me to both learn a lot and meet all the people from this list. Accurate and precise preclinical imaging methodologies are incredibly important in the detection of cancer. These methodologies help determine different diagnoses, prognoses, and stratification of patients into treatment groups. The first one I'm going to go over is bioluminescence. Bioluminescence is a type of optical molecular imaging that, on the electromagnetic spectrum seen to the left of the screen, uses visible light. More specifically, this imaging uses luciferase, which is found in fireflies, to detect light energy that is released and then detected by a program and translated into an image. While it's high in sensitivity, it's often low in resolution and depth dependent, and additionally, you'd never use bioluminescence in the clinic because of how it does rely on luciferase, so it's really just for preclinical applications. Next is positron emission tomography, also known as PET scans. PET scans use gamma rays and are a form of nuclear molecular imaging. For this method, you're injecting your radionuclide of choice, which then accumulates in your desired tissue. From here, the machine is able to detect that gamma radiation and produce an image. Last is magnetic resonance imaging, or MRI, a form of anatomical imaging. An MRI uses magnets and radio frequency signals to collect data that is then translated into an image. An emerging type of imaging that I spent my time on the last 6 months is Raman spectroscopy. Similar to bioluminescence, Raman uses visible light. More specifically, how Raman spectroscopy actually works is that the bonds of a molecule are constantly vibrating inside, and when you shine a laser on them, the photons from the light are going to hit that molecule and scatter at different frequencies, depending on what that bond is. So some of the scatter is filtered out, and what you're going to be left with is the Raman scatter. You're then able to collect this through a lens and produce a spectra that is specific to the region of interest under study. So that's what these three are here. Raman spectroscopy is a type of vibrational spectroscopy, so the peaks are vibrations, and what they're showing is a change in frequency, which allows you to differentiate between different compounds. So now you just travel point by point across the object, collecting the spectra at each point. And from all these different spectra, you're able to create a false color map or image, like the one seen on the right, that represents all of these points, telling you what makes up your object of interest. Here we can see the spectra of 3 different dyes that we use in our lab. From these peaks of interest, we can create a false color image by associating different peaks with a specific color and produce that image like the one on the right again. So for example, the purple would be composed of the spectra from dye 1 and so on. Multiplexing is looking at different dyes. This is what Raman is really good for. So you can image multiple targets at once because the spectra is so unique to each dye. Whereas with something like fluorescence, you can only look at one thing at a time. So each single frequency is how you get a nice, distinct spectra. Despite this advantage, one limitation to Raman spectroscopy is a depth limitation. So here first is an original Raman spectrophotometer, and then taking into consideration the concept of photon migration to collect the Raman signal, spatially offset Raman spectroscopy overcomes the depth limitation by separating the collection location from the point of excitation, allowing for probing deeper into the tissue. And here to the right is a spatially offset Raman spectrophotometer designed by Faye Nicholson. Additionally, a contrast agent is often needed, as the intensity of the signal in Raman spectroscopy can often be weak. So the contrast agent that we spent time improving upon these past 6 months are the surface-enhanced resonance Raman scattering nanostars, also known as SIRS nanostars. The components of the base of these nanostars are ascorbic acid, water, gold seeds, and gold ions. At the center of these stars are the gold seeds, and then the ascorbic acid and gold ions are competing for surface space on the seeds. Ascorbic acid brings on a negative charge to the star, and then the gold ions visually make up the points of the star-like shape. So when these are added into the reaction is when the star shape actually forms. On the UV spectrum, A star shape, which is more what we want again, is associated with a visibly blue color, while a circular shape will be more red. So these are two separate batches of nanostars. This blue batch is going to be composed of more hard-shaped stars, whereas this more purple-looking batch are going to have rounder edges like a circle. So with that in mind, in this video I am adding the gold ions, and as you can see, the solution immediately turns blue, meaning that the stars are immediately forming when I'm adding these gold ions. Once you create the star, you are then able to put a marker on the surface and functionalize the nanoparticles to locate something on the cell surface, like a tumor. However, your ability to functionalize the nanoparticle depends on the amount of reagents you are using. So for example, as I said, ascorbic acid brings on a negative charge on the star, as you can see. So although using more ascorbic acid will benefit certain characteristics of these stars, having too much of that negative charge is going to impede the nanostar's ability to react with different markers that we're going to use to functionalize it. Again, the different amounts of reagents that you add, the different characteristics that you're going to produce. One of the problems that we came into contact with was with the UV. Again, we want a more blue color, meaning a more star-like shape. A bluer color will show up as roughly above 600 on the UV spectrum, while a redder color will be lower than that. Here I've averaged 5 batches together using a protocol using 254 grams of ascorbic acid, and then also averaged 5 batches together utilizing a protocol that used 63.5 grams of ascorbic acid. As we can see by the trend, using more ascorbic acid creates more of a bluer color. However, still using 63.5 grams of ascorbic acid, it still has a blue color, it's just to a lesser degree. And then to the right of this graph, I have images of the actual stars. So with more ascorbic acid, you can see that there's a more defined star shape. There are harder edges on these stars. But with this less ascorbic acid, we still do have points on the stars, they're just more rounded edges. With this bluer color from the greatly increased ascorbic acid amount, provides a much greater negative charge on the surface of the molecule, as ascorbic acid has a negative charge. As I mentioned before, this negatively affects our ability to functionalize the nanoparticle. Additionally, though, it also negatively affects the concentration, as seen below in this cartoon, because of how each negatively charged particle is going to be repelling each other because both of them have a negative charge on the outside. Again, this chart is comprised of the averages of 5 batches from a protocol using 254 grams of ascorbic acid, and then again 5 batches averaged together using a protocol of 63.5 grams of ascorbic acid. As we can see with this trend, the lower the amount of ascorbic acid, the higher the concentration, as there is less of a negative charge on the stars. And then in these two videos, we can see that the concentrations are greatly different. So with more ascorbic acid compared to less ascorbic acid, we can see just how many more stars there are in a batch with the less ascorbic acid because of that lessened negative charge. So what happens after we make these nanoparticles? In this case, the nanoparticles were tested in 5 mice with glioblastomas. First, targeted RGD nanoparticles of a concentration of 10 nanomolar were used on 2 mice, and in both cases, the signal was way too strong and the nanoparticles were everywhere. In the bloodstream, all over the head, so there was no way to distinguish between tumor and not tumor. Next, non-targeted nanoparticles with just PEG on the surface with a concentration of 5 nanomolar were used on 1 mouse, and targeted RGD nanoparticles, also with a concentration of 5 nanomolar, were used in another. In both of these cases, the signal was still too strong, but to a lesser degree than the first 2 mice. Finally, with the last mouse available, non-targeted nanoparticles with just PEG on the surface with a concentration of 2.5 nanomolar were used. And here the signal was a good amount. And below, we can see the MRI images of the tumor, and next to it, a Raman imaging of the actual tumor. So now that a good area of concentration is now known, doing future work to validate this in vivo is the next goal. I'd like to thank the Dana-Farber Cancer Institute for allowing me to do research at their facility, as well as the CaNCURE Foundation, specifically Anne for organizing and meeting with all of us and putting together a great list of guest speakers.